At first, the weather system appeared routine. Meteorologists monitoring atmospheric conditions across a broad region observed a developing area of instability moving steadily through the atmosphere. Similar patterns emerge many times each year, often producing little more than scattered thunderstorms, brief periods of heavy rain, and isolated wind gusts. Nothing about the initial observations immediately suggested a major crisis. Forecast models showed a potentially active weather period, but not one that stood out dramatically from countless other weather events. Yet within days, meteorologists began noticing subtle but important changes. New data revealed stronger atmospheric energy, increasing moisture levels, and environmental conditions that were becoming unusually favorable for severe weather development. What initially seemed ordinary was rapidly evolving into something far more concerning. Weather forecasting relies on the continuous analysis of thousands of observations collected from satellites, weather stations, radar networks, aircraft, ocean buoys, and atmospheric sensors. These observations allow meteorologists to monitor the atmosphere in extraordinary detail. As updated information arrived, experts noticed that multiple ingredients required for dangerous weather were beginning to align simultaneously. Warm, moisture-rich air was spreading across the region near the surface. Higher in the atmosphere, powerful winds were strengthening. Temperature differences between air masses were increasing. These factors alone do not guarantee severe weather, but when they combine in the right way, they can create an environment capable of producing widespread hazardous conditions. One of the first warning signs involved atmospheric instability. Instability occurs when warm air near the surface rises rapidly into cooler air higher in the atmosphere. This rising motion serves as the fuel for thunderstorms. The greater the instability, the more energy storms can access. Meteorologists examining forecast data observed values that were steadily increasing. Areas that initially appeared only moderately unstable were becoming significantly more energized. Such conditions often support stronger thunderstorm development, particularly when combined with favorable wind patterns. At the same time, moisture levels throughout the lower atmosphere continued rising. Moisture plays a critical role in severe weather formation because it provides the water vapor necessary for cloud and thunderstorm development. Warm air can hold large amounts of moisture, and when that moisture condenses into clouds and precipitation, enormous quantities of energy are released into the atmosphere. Forecasters noticed that humidity values across large areas were reaching levels often associated with significant weather outbreaks. The atmosphere was becoming increasingly capable of supporting powerful storm systems. Another important factor was wind shear. Wind shear refers to changes in wind speed and direction with height. Strong wind shear can help thunderstorms organize into long-lasting and potentially dangerous structures. While weak storms may collapse quickly, storms developing within a highly sheared environment can persist for hours and grow considerably stronger. Forecast models indicated that wind shear values were increasing across the region. This development raised concerns because it suggested that any storms that formed would have the potential to become severe. Meteorologists began comparing the evolving environment to historical weather events. Although no two situations are identical, certain atmospheric patterns have repeatedly been associated with significant severe weather outbreaks. Several forecast indicators showed similarities to previous events that produced damaging winds, large hail, intense thunderstorms, and tornadoes. While experts remained cautious about drawing direct comparisons, the growing resemblance to past severe weather episodes attracted attention within forecasting centers. Radar imagery initially showed only scattered areas of precipitation. However, as conditions continued evolving, storm development became increasingly organized. Clusters of thunderstorms began appearing along boundaries separating different air masses. Some storms quickly intensified, producing stronger radar signatures that suggested vigorous upward motion. Meteorologists closely monitored these developments because they often provide early clues regarding how a weather event may evolve over the coming hours. Forecast discussions gradually adopted a more urgent tone. Rather than focusing solely on isolated severe storms, meteorologists began considering the possibility of a broader regional event. Multiple forecast models showed conditions remaining favorable for storm development across a large geographic area. This increased the potential for widespread impacts rather than localized incidents. Emergency management agencies received updated briefings outlining possible scenarios, while forecasters continued refining their assessments using the latest available data. One reason severe weather forecasting remains challenging is the atmosphere's complexity. Small changes in temperature, moisture, wind patterns, or storm interactions can significantly alter outcomes. A slight shift in a weather boundary may determine where storms become strongest. Minor variations in atmospheric moisture can influence storm intensity. Because of these factors, meteorologists continuously evaluate new observations and adjust forecasts as conditions evolve. The developing crisis required constant monitoring because even subtle atmospheric changes could affect the severity and location of potential impacts. As satellite imagery provided additional insight, meteorologists observed strengthening upper-level weather systems approaching the region. These systems often act as catalysts for severe weather outbreaks by enhancing atmospheric lift and increasing wind dynamics. The interaction between surface conditions and upper-level features appeared increasingly favorable for widespread thunderstorm development. Forecasters recognized that the atmosphere was becoming primed for a significant event if current trends continued. Public awareness began increasing as weather agencies issued updated outlooks. Residents across potentially affected areas were encouraged to monitor forecasts closely and review emergency preparedness plans. Meteorologists emphasize that severe weather can develop rapidly and that advanced preparation often improves safety outcomes. While the exact details of the event remained uncertain, confidence was growing that conditions would support at least some degree of significant weather activity. One of the major concerns involved the potential for damaging straight-line winds. Many people associate severe weather primarily with tornadoes, but widespread wind damage can affect much larger areas. Powerful thunderstorm winds are capable of downing trees, damaging structures, disrupting power infrastructure, and creating dangerous travel conditions. Forecast models indicated that atmospheric conditions could support organized storm systems capable of producing extensive wind impacts over large regions. Large hail also emerged as a concern. Strong updrafts within severe thunderstorms can lift water droplets high into extremely cold portions of the atmosphere, where they freeze and grow into hailstones. The stronger the updraft, the larger hailstones can become. Meteorologists analyzing instability and wind profiles observed conditions that could potentially support significant hail development in the strongest storms. Such hail can damage vehicles, roofs, crops, and other property. Perhaps the most closely watched threat involved tornado potential. Tornado formation requires a specific combination of atmospheric ingredients, including instability, moisture, lift, and wind shear. Forecast data suggested that several of these ingredients would be present simultaneously across portions of the region. While predicting the exact location of tornadoes remains impossible far in advance, meteorologists recognize that the environment could support rotating thunderstorms capable of producing tornadoes under favorable circumstances. As the forecast period approached, confidence continued increasing that a significant weather event was developing. Meteorological agencies expanded monitoring operations and prepared to issue warnings as necessary. Emergency managers coordinated with local officials to ensure readiness. Utility companies reviewed response plans in case widespread outages occurred. Transportation agencies evaluated potential impacts on road and air travel. Preparations accelerated as concern grew regarding the developing situation. Forecast model agreement also improved. While differences remained regarding specific details, numerous independent models showed similar trends. This consistency strengthened confidence that atmospheric conditions would become increasingly favorable for severe weather. Forecasters still emphasized uncertainty regarding exact impacts, but the overall message became clearer with each update. The environment was becoming more dangerous, and the potential for widespread severe weather was increasing. Nighttime observations provided additional evidence that conditions were evolving as expected. Weather balloons launched from multiple locations measured atmospheric profiles that closely matched concerning forecast projections. Moisture levels remained elevated. Wind shear continued strengthening. Instability values increased further. These observations confirmed that the atmosphere was moving toward a state capable of supporting significant thunderstorm development. Meteorologists understand that severe weather crises rarely emerge from a single factor. Instead, they develop when multiple atmospheric ingredients align simultaneously over large areas. In this case, nearly every critical ingredient appeared to be strengthening. Moisture was increasing. Instability was rising. Wind shear was becoming more favorable. Upper-level support was approaching. Forecast confidence was growing. Together, these developments painted an increasingly concerning picture. By the latest forecast cycle, what had once appeared to be an ordinary weather pattern had transformed into a situation demanding close attention. Weather experts across forecasting centers agreed that conditions were becoming increasingly supportive of severe thunderstorms and potentially dangerous impacts. Although uncertainty remained regarding the exact magnitude and location of the worst conditions, the overall trend was unmistakable. The atmosphere was organizing itself into a configuration capable of producing significant weather hazards. Meteorologists continued monitoring every new observation, every radar scan, every satellite image, and every model update because the situation remained dynamic. With environmental conditions continuing to strengthen and warning signs becoming more numerous, experts delivered a message that was both clear and increasingly urgent. A severe weather crisis appeared to be developing, and the coming period could prove significantly more dangerous than initial forecasts had suggested. As meteorologists continued analyzing incoming data, concern grew steadily across forecasting centers. The atmospheric ingredients that had been developing over previous days were no longer merely theoretical possibilities appearing in computer models. Real-world observations now confirmed that the environment was becoming increasingly favorable for dangerous weather. Weather balloons launched throughout the region reported significant instability, elevated moisture levels, and strengthening winds at multiple altitudes. Radar systems began detecting expanding areas of thunderstorm development, while satellite imagery revealed growing cloud formations spreading across key sections of the forecast area. The evolving situation suggested that the atmosphere was moving closer to a point where severe weather could develop rapidly and affect large populations. One of the most concerning aspects of the situation involved the sheer geographic scale of the developing weather pattern. Severe weather events are often localized, affecting relatively small areas before weakening or moving away. In this case, however, atmospheric conditions favorable for storm development extended across hundreds of kilometers. Forecasters observed a broad corridor of warm, moisture-rich air interacting with cooler, drier air masses. This type of setup frequently creates strong boundaries that serve as focal points for thunderstorm formation. As these air masses collided, rising motion increased throughout the atmosphere, creating an environment capable of supporting numerous storms simultaneously. Meteorologists paid close attention to the strengthening jet stream overhead. The jet stream consists of fast-moving winds high in the atmosphere that influence weather patterns across vast regions. During severe weather outbreaks, the position and intensity of the jet stream can significantly affect storm organization and longevity. Forecast data indicated that a particularly strong upper-level wind pattern was moving into alignment with surface conditions. This combination often supports organized storm structures, capable of producing widespread impacts. The interaction between upper-level dynamics and lower atmospheric instability became one of the central concerns discussed in forecast briefings. As the day progressed, thunderstorms began developing with greater frequency and intensity. Initially, many storms remained relatively isolated. However, meteorologists noticed that some cells were strengthening more rapidly than expected. Radar imagery revealed powerful updrafts within several storms, suggesting vigorous vertical motion and substantial atmospheric energy. Strong updrafts are critical because they help storms sustain themselves, allowing them to produce severe weather over longer periods. The stronger these upward motions become, the greater the potential for damaging winds, large hail, and other hazards. Emergency management agencies across potentially affected areas increased their readiness levels. Local governments reviewed communication procedures, emergency response plans, and resource allocation strategies. Utility companies positioned repair crews in anticipation of possible power outages. Transportation authorities monitored weather forecasts closely, recognizing that severe storms could disrupt road networks, rail operations, and air travel. Hospitals and emergency services evaluated staffing requirements in case severe conditions generated increased demand for assistance. Although the exact impacts remained uncertain, preparations intensified as confidence in the developing threat continued growing. One challenge associated with severe weather forecasting involves timing. Atmospheric conditions may remain favorable for many hours before storms fully utilize available energy. Forecasters recognize that this event could evolve in stages. Initial thunderstorms might serve as precursors to larger storm complexes developing later. Alternatively, isolated storms could merge into more organized systems capable of affecting broader areas. Because severe weather often evolves rapidly, meteorologists continuously updated forecasts as new observations became available. Every radar scan and satellite image contributed valuable information regarding how the atmosphere was responding. Wind profiles throughout the atmosphere became increasingly supportive of rotating thunderstorms. Meteorologists use specialized data to evaluate how wind direction and speed change with altitude. Certain combinations of these factors can promote storm rotation, increasing the likelihood that thunderstorms become long-lived and potentially dangerous. Forecast models and direct observations suggested that several areas would experience favorable wind conditions during the peak period of instability. This raised concerns regarding the possibility of organized severe storms capable of producing significant impacts. As afternoon heating intensified, atmospheric instability increased further. Solar energy warmed the surface, causing air temperatures to rise across large portions of the region. Warm air near the ground became increasingly buoyant, providing additional fuel for thunderstorm development. Forecasters observed instability values reaching levels commonly associated with severe weather outbreaks. Combined with abundant moisture and favorable wind dynamics, these conditions created a highly volatile environment. Meteorologists emphasized that storms forming within such an atmosphere could intensify quickly and produce hazardous conditions with limited warning. Large hail emerged as a growing concern as several storms displayed radar signatures associated with strong updrafts. Hail forms when powerful upward currents repeatedly lift water droplets through freezing layers within thunderstorms. Each cycle allows ice particles to accumulate additional layers before eventually falling to the ground. In particularly intense storms, hailstones can become large enough to damage vehicles, roofs, crops, and infrastructure. Forecast discussions increasingly highlighted this threat as atmospheric conditions continued supporting vigorous storm development. At the same time, forecasters monitored the risk of widespread damaging winds. Organized thunderstorm systems can generate powerful outflow winds capable of affecting extensive areas. Unlike tornadoes, which typically impact relatively narrow paths, severe straight-line winds can cause damage across broad regions. Falling trees, damaged power lines, structural impacts, and transportation disruptions often result from such events. Several forecast models indicated that storms might eventually organize into larger complexes capable of producing significant wind-related impacts. The possibility of flash flooding also gained attention. Moisture levels throughout the atmosphere remained exceptionally high, increasing the efficiency of rainfall production. When thunderstorms develop in moisture-rich environments, rainfall rates can become extremely intense. Urban areas are particularly vulnerable because paved surfaces limit water absorption, allowing runoff to accumulate rapidly. Rivers, streams, and drainage systems may become overwhelmed if heavy rainfall persists. Meteorologists identified several regions where repeated thunderstorm activity could increase flood risk considerably. Satellite imagery provided further evidence that atmospheric conditions were becoming increasingly unstable. Expanding cloud fields indicated widespread upward motion across portions of the forecast area. Infrared imagery revealed rapidly cooling cloud tops associated with strengthening thunderstorms. Such observations often signal intensifying storm activity and help forecasters identify areas where severe weather may soon develop. Combined with radar and surface observations, satellite data painted a picture of an atmosphere becoming progressively more active and volatile. As evening approached, storm coverage expanded significantly. Thunderstorms that had previously remained isolated began interacting with one another. Some merged into larger clusters, while others developed along newly formed boundaries created by earlier storm activity. These interactions can sometimes enhance storm intensity by concentrating atmospheric energy and modifying local environmental conditions. Meteorologists carefully tracked these developments because they often influence the evolution of severe weather outbreaks. Forecast offices issued increasingly urgent updates emphasizing the need for public awareness. Meteorologists reminded residents that severe weather can develop rapidly and that conditions may change within minutes. Reliable access to warnings became particularly important given the dynamic nature of the event. Emergency communication systems, weather radios, mobile alerts, and local media outlets played critical roles in ensuring that information reached affected communities quickly. The overnight period presented additional challenges. Severe weather occurring after dark often poses increased risks because visibility is reduced and many people are asleep. Forecasters noted that atmospheric conditions would likely remain favorable well into the night. Unlike some weather events that weaken after sunset, this system appeared capable of sustaining significant activity due to strong upper-level support and abundant atmospheric energy. Emergency managers emphasized the importance of maintaining awareness throughout the night and ensuring that warning methods remained accessible. Weather models continued indicating that the broader pattern responsible for the event was unlikely to disappear immediately. While individual storms would eventually weaken, the larger atmospheric setup remained in place. This raised concerns that severe weather could continue affecting portions of the region over an extended period. Meteorologists examined future forecast cycles closely, searching for indications regarding how long favorable conditions might persist and whether additional rounds of storms could develop. The combination of multiple hazards made the situation particularly complex. Damaging winds, large hail, flash flooding, and the potential for tornadoes all remained possible within the evolving environment. Different areas face different levels of risk depending on local atmospheric conditions and storm behavior. This complexity required careful communication to ensure that communities understood the range of possible impacts without focusing exclusively on a single threat. By the latest forecast updates, meteorologists agreed that the situation had evolved far beyond the ordinary weather pattern initially observed days earlier. What began as a developing area of atmospheric instability had transformed into a significant, severe weather threat affecting a broad region. Every major forecasting indicator pointed toward an environment capable of supporting dangerous storms. Instability remained elevated. Moisture levels stayed unusually high. Wind shear continued providing organizational support. Upper-level dynamics remained favorable. Radar and satellite observations confirmed active storm development across multiple areas. As forecasters reviewed the latest data, their message became increasingly clear. The severe weather crisis they had been monitoring was no longer simply a future possibility. Conditions supporting hazardous weather were actively developing. Storms were becoming stronger, and the potential for widespread impacts continued increasing. Meteorologists remained focused on tracking every change within the atmosphere because the situation was still evolving. Yet, despite ongoing uncertainties regarding exact storm paths and local impacts, one conclusion stood out above all others. The atmosphere had entered a highly dangerous state, and the severe weather threat was growing more significant with each passing hour.